In the last example, we talked about an algorithm that we can use to find the eigenvalues and eigenvectors of a matrix. So now, I would like to talk about why we do what we do. You see, the equation that we would like to solve is just this, AV equal to lambda V. However, this is more complicated than it looks because this A here, this is a matrix, but my V, this is a vector. My V here, this is a vector. And the lambda here, this is a number. So we actually have things from different class being multiplied together. And what makes it worse is that we only know the matrix A here, the vector V, and the number lambda. These are unknown. So it seems like we have two unknowns here. Now, one thing that we can try though is that, well, we have AV equal to lambda V, right? Why don't we move lambda V to the other side so that we can factor the V out? So I'm gonna get AV minus lambda V equal to 0. So then A minus lambda times V equal to 0. However, this doesn't work because my A is a matrix, but my lambda is a number. I can't just subtract a number from a matrix. However, I can try something similar though. I can first replace this vector V here. I can substitute this with the identity matrix I times V. If I multiply the identity matrix to a vector, then I get the same vector. So if I make a substitute, I'm gonna have that A times V equal lambda times IV. Now, I can look at this V as a vector, and then my A is a matrix. And if I look at the right hand side, lambda times I, even though lambda is a number, but if I multiply a number to a matrix, I'm gonna get a matrix now. So it seems like on both sides of my equation, I'm gonna have some kind of matrix multiplied to a vector V. So I can try to do what we did earlier. I'm gonna have A times V minus lambda I times V equal to 0. And then I can factor out the V. I'm gonna have that V multiplied by A minus lambda I equal to 0, where my V, this is a vector, my A is a matrix, and lambda times I is also a matrix. But now, if we look at this equation again, remember that V, this is the unknown. So it would seem like the whole thing that we are looking, this is just one big system of linear equations. This is just a system of equations. We have this pink matrix. I would just like to solve for this unknown. I have this system, pink matrix times V equal to the 0 vector. So in the end, what we are trying to do is we are just trying to solve for this system. I'm gonna have A minus lambda I, and then the right hand side is gonna be just the 0 vector. If I were to write the augmented matrix form for this system of equation, this is what I'm gonna have. However, note that this system always have a solution because the right hand side is 0. So I can always have a 0 solution. However, I don't want my vector V to be 0 because an eigenvector cannot be 0. So I don't want to just solve it. I want to solve for a non-zero solution. However, there is one thing that we see from lecture 6 is that if this system has a non-zero solution, then what we are gonna need is that we're gonna need this pink matrix to have a 0 determinant. I'm gonna need the determinant of A minus lambda I to equal to 0. So by some kind of twist of fate, because I want my system to have a non-zero solution, that becomes a determinant problem. I would like the determinant of this matrix to be 0. But if we remember again, this lambda, this is a number. This lambda, this is actually unknown. So what I would like to do in the end is that I need to find the value of lambda that makes this determinant 0. In other words, my lambda, the eigenvalue, is going to be a solution to this equation, the determinant of A minus xi has to equal to 0. And now, this is why we do what we do in the algorithm. We have this characteristic polynomial and we need to set it to be equal to 0. The solution to that is going to be my eigenvalues. And in the end, I actually have to solve for a system of equation where my matrix is going to be just A minus lambda I, and the solution to that is going to be my eigenvectors.